No fiberglass, no spray foam, no vapor barrier. One fire, and it kept the family alive through every winter for 40 years. The engineers who designed $300,000 modern cabins are now copying what these builders did with axes. In the winter of 1851, in the upper Mississippi Valley, a family of 5 survived a January that dropped to negative 15 degrees Fahrenheit outside their walls. Inside, the cabin held 58 degrees. No insulation as we know it today. No weather stripping, no double-pane glass. Just logs and something else. Something the builders understood that we forgot, and that modern engineers are now measuring all over again. These cabins were built fast. A skilled crew, or a single family with good neighbors, could raise the walls in a weekend. The trees were cut within a mile of the site. The logs were hewn flat on 2 sides and stacked green, meaning the wood hadn't dried yet. The gaps between logs were chinked with moss, clay, horsehair, whatever the land offered. No hardware store. No building code. No engineer on site. And yet, reconstructions of these cabins by researchers at the University of Manitoba and at several living history sites across the American Midwest show something that stops people cold. These structures, in documented winter conditions, used 30% less energy than a modern cabin of the same footprint, built to current R-value standards. 30% less with no insulation. How? To understand that, you need to forget everything you were taught about warmth. Modern building science measures comfort in one number: air temperature. 70 degrees Fahrenheit, that's the target. The thermostat reads 70, and the building is declared comfortable. But your body doesn't read air temperature. Your body reads radiant exchange. Think about standing outside on a clear winter morning, 10 degrees Fahrenheit, but the sun is out, full and low and direct on your face. You feel warm. The air temperature hasn't changed. What changed? What changed is the radiant energy reaching your skin. Now think about standing in a modern open-plan cabin, air temperature 68 degrees, 12-foot ceilings, large north-facing windows, no fire, just a baseboard heater running in the corner. You feel cold. Not because the thermometer says cold, because nothing is radiating heat toward your body. The pioneer builders didn't have the vocabulary for radiant exchange, but they had the results. And the results told them exactly what to build. The first principle was the log itself. Not for insulation, but for mass. A 12-inch green log, freshly hewn from white pine or spruce, has an R value of roughly 2. That's terrible by modern standards. A 4-inch bat of fiberglass gives you 13. So by the numbers, the pioneer cabin wall loses catastrophically. And it does lose heat through the wall. But the log is also a battery. A 12-inch log, at 60 pounds per cubic foot, stores heat at a rate that fiberglass simply cannot match. When the fire burns through the evening, the logs absorb that heat, slowly, the way stone absorbs the sun. Then the fire dies or is banked low, and the logs begin to release. The technical term is thermal lag. The heat that entered the log at 8 in the evening doesn't come out the other side until 4 in the morning, when the fire is cold and the outside is at its lowest point. The wall isn't insulating the cold out, it's delaying it. And in that delay, the family sleeps. The second principle was the ceiling. 7 feet. 7 feet was standard in a pioneer cabin. Today that feels oppressive. We build at 9 feet. 10 12 in showrooms and open-plan retreats. And we pay for it, every single month. Here's the physics. Warm air rises. Not gently, it rises aggressively. In a room with a 12-foot ceiling, the air at head height and the air at the ceiling can differ by 12 to 18 degrees Fahrenheit. That's not a comfort zone up there. That's a waste zone. Every BTU that drifts up past 8 feet is a BTU that never reached a human body. The pioneer builder didn't know the word BTU, but they knew that a low ceiling meant the fire's heat stayed where the people were. 7 feet of air column warms faster than 12, holds that warmth longer, and costs less fire to maintain. The ceiling wasn't a limitation. It was a decision. The third principle was the fire itself. Not what burned, but where it was. The pioneer hearth was central or close to central in the main room. And it was stone. Always stone. Stone chimney. A stone hearth surround. Sometimes a masonry firebox built up from the floor. Not for decoration. For mass, again. A stone chimney chase running through the center of a cabin, 18 inches square. Absorbs heat during the burning cycle and radiates that heat back. For 8 to 12 hours after the fire goes out. The chimney is not a chimney. The chimney is a battery. The fire charges it, and the cabin runs on stored radiation through the night. Your body, 6 feet from that stone mass, receives infrared, direct, the way you'd receive heat from a cast iron stove, or from the sun on your face on a clear morning. The air in the room might be 55 degrees, but the radiant temperature your skin perceives is 70 or more. Two different things. The pioneers were heating bodies, not air. And then there's the fourth principle, the one that's hardest for modern people to accept. Small windows. Pioneers were not poor glazers by accident. They were not limited by technology alone. Small windows in a pioneer cabin were a calculated trade. Every square foot of single-pane glass loses heat at a rate roughly 12 times faster than the log wall beside it. The builders understood this, not in British thermal units, but in cords of wood. More window means more wood. The north wall and the west wall might have no window at all. A single east-facing window for morning light. A small south window for passive solar gain in the afternoon. The window wasn't a view. The window was a calculated hole in the thermal envelope, sized to let in exactly as much light as the family needed, and no more cold than the fire could replace. Now here is where the modern misreading happens. When engineers evaluate pioneer cabins today, they run the numbers on the wall. R value 2, they write. Poor thermal envelope. R, they conclude. And they move on. What they missed is that the wall was never meant to carry the thermal load alone. The system was 4 things working together. High-mass logs that store and delay. Low ceiling that holds the warmth at body height. Central radiant source that heats bodies directly, not air. Minimal glazing that limits thermal escape. Remove any one of those 4, and the system degrades. Remove 2, and it fails. This is the invisible error in every modern log cabin that copies the look, but not the logic. 12-foot ceilings. Electric baseboard heat. Floor-to-ceiling windows facing west. Logs that are decorative, not structural mass. The result is a building that consumes 4 times the energy of the original it was inspired by, because it copied the material, not the system. The researchers at the University of Manitoba built a test structure in 2009. Full-scale reconstruction. Original dimensions. Original log species. Original chinking method. Original central hearth. Original ceiling height. They ran it through a monitored winter. What they found was not efficiency in the way a passive house is efficient. What they found was stability. The interior temperature oscillated within a 6-degree range across a 24-hour cycle, even when outside temperatures swung by 35 degrees in the same period. The logs, the ceiling, the stone mass were acting as a flywheel, absorbing peak inputs, releasing slowly, smoothing the curve. Modern construction, with its thin walls, high ceilings, and electric heat, tracks the outside temperature almost instantly. Every spike in cold outside is a spike in energy demand inside. The pioneer cabin never saw the spike. Now, 3 principles that you can apply today, not as folklore, as physics. The first is perceived ceiling. If you have a space with a ceiling above 9 feet and you're heating it in winter, consider a dropped soffit or a board and batten panel running across the center of the room at 7 or 7.5 feet. You don't close the full ceiling. You create a lower zone where the heat collects above the furniture at the height where bodies are. The warm air stratification above the soffit, a belve of where comes buffer mass, not waste. This costs $200 to $400 in lumber and reduces perceived heating demand in that space by a measurable amount in the first winter. The second principle is central radiant mass. If you have a fireplace or a wood stove against an exterior wall, it is working against you. The heat it generates radiates in all directions. Half of it goes into the wall and out. A central stove, or better, a masonry heater in the center of the floor plan, radiates heat into the living volume, not into the exterior. Modern masonry heaters, descendants of the Finnish contraflow stove and the Russian PEC, burn for 2 to 3 hours and radiate for 18 to 24. A single loading, morning or evening, heats the stone, and the stone heats the house. The fire is not the heater. The stone is the heater. The fire just charges it. The third principle is glazing audit. Walk your cabin or farmhouse in January at 10 in the morning. Put your hand 6 inches from each window, not touching the glass, 6 inches away. You will feel cold air falling, a convective draft, off every single pane. Double pane modern glass stops most of this. Single pane does not. But even modern double pane glazing on north and west exposures costs you more than it gives you in a heating-dominated climate. The pioneer answer was to minimize those openings. The modern answer is to at least cover them at night with a heavy insulating curtain. A $4 curtain on a north window reduces that window's heat loss by 40 to 60% from 6 p.m. to 8 a.m. The fix is not expensive. The fix is understanding which openings are costing you and when. There is one more thing worth saying before we close. The pioneer cabin was not comfortable by modern standards. The smoke from an open hearth was a health hazard. Fire risk was constant. Sanitation was primitive. None of that is romanticized here. What we're looking at is not a lifestyle to return to. What we're looking at is a thermal logic embedded in a structure built without engineering degrees or building science conferences that solved problems we are still paying to solve today. The pioneer family wasn't surviving in spite of their cabin. They were surviving because of it. Because someone, at some point, figured out that logs hold heat. Low ceilings concentrate it. stone releases it slowly, and small holes lose at last. 4. Variables. One system. Working together. That knowledge was never published. It was never patented. It was passed from axe crew to axe crew, from family to family, across 100 years of northern winters. And then, somewhere in the 20th century, we got cheap heating fuel, and we stopped needing to know. The engineers who study these structures now are not discovering something new. They are remembering something old, and the physics hasn't changed. The physics never changes. Before you add force, read the flow. The fix was always there. You just couldn't see it.